We'll get started, and we're going to continue today what we started on Monday, related to the initial fluid distribution in a reservoir, petroleum reservoir. Just as a summary, we have this calculation of initial fluid in place from an equation that is usually written for oil, and this is surface oil as the average thickness times the average porosity times 1 minus the average connate water saturation. This gives us, we have some kind of an average area. This gives us the, I'll write this a little bit different here. The term here is what we refer to as the reservoir pore volume. And the entire term, including the 1 minus water saturation, this is representing the average oil saturation, if we're talking about getting the initial oil in place. The entire term here is what we call the hydrocarbon pore volume. In this case, the hydrocarbon is oil. For the reservoir oil. This entire term. So we're still talking about cubic meters in the reservoir, cubic meters of oil, of reservoir oil in the reservoir. So we've got the pore volume, the oil volume, but this is all at reservoir conditions, maybe 300 bar, 100 degrees C, might be 900 bar, 130 degrees C. But what we're looking for is the surface oil. So we take this term here and divide it by what we call formation volume factor. Okay? BO. This is the, I'll just write it down here, BO is the oil formation volume factor. And it's defined as the ratio of a cubic meter of reservoir oil. If you start with 1 cubic meter of reservoir oil, you end up with so many cubic meters of surface oil. It's this ratio. Reservoir oil volume divided by the surface oil volume. And we're interested in this particular conversion factor at initial pressure because we're looking at the initial oil in place. And the BO term is pressure dependent. If we go to a lower pressure as the reservoir depletes, that ratio will change. So we're looking at a very specific, at initial conditions, to calculate this initial oil in place. Okay? Okay. So we've got a pore volume. If this is our reservoir, of course what you see is the bulk volume. The pore volume is this bulk volume times the porosity. And you remember what kind of porosity the chalk has? It's very unusual, up in the 40% range. That's this first term. You know, thickness, that could be the height. The area would be the circular area. And then the porosity, the average porosity might be 42% of this piece of chalk. That would be the pore volume. And then we say that whatever is not water is hydrocarbon. And since we're looking only at the oil right now, we're looking at the oil saturation. And of course the oil saturation in this piece of chalk is 0. Of course so there's no oil and there's no water. But if you fill this in the Ekofisk field, the same piece of chalk would have about 10% water saturation. 10% of the pore volume would be water. 90% would be oil. So it's a lot of oil per piece of rock because you have a high porosity and a high oil saturation. That's this term on the top, the numerator. The term on the bottom, it says that initially in Ekofisk, this is at 7,000 psi, pounds per square inch, which is like, I don't know, 400 and some bar, 130 degrees C. If we take 1 cubic meter of oil in the Ekofisk field, initially in 1970, to the surface, how much oil do you think we get into the tank? Just intuitively. For the non-petroleum engineers in the group. How much do you think you get? Do you get more oil? You get like two cubic meters? Yeah? Okay, so you're saying, so there's gas dissolved in the oil, and that's in almost all reservoirs. There's this, it's like the soda pop, the Coca-Cola you buy. There's CO2 dissolved in the water. Well, in petroleum reservoirs, there's natural gas dissolved in the oil. What's your name? Huh? Nikolai? What Nikolai is saying is that in the reservoir in Ekofisk, there's about, remember I talked about it on Monday, 300 standard cubic meters of surface gas for every standard cubic meter of surface oil. So if I start with 1 cubic meter in Ekofisk reservoir oil down in the reservoir, what I will get at the surface is about a half of a cubic meter into the tank that I can sell. Half of it. So that BO is what? 2. About 2 for Ekofisk. It can be as high as 3, and it can be as low as 1.1. We call that shrinkage. So the shrinkage of the Ekofisk oil is a factor of 2, right? It shrinks by 50%. Where does that 50% go? We know that there's conservation of mass. How much surface gas do I get from 1 reservoir cubic meter of oil? How much surface gas do I get? If I get 300 standard cubic meters surface gas for every 1 cubic meter of surface oil, but I'm only getting out a half a cubic meter of surface oil, right? So I get 150 standard cubic meters. So that shrinkage factor of 2 is related, as Nikolai said, to this 150 standard cubic meters coming out of the oil. If you go to the soda pop machine and you buy Coca-Cola, you shake it up, you get rid of all of the CO2, does it shrink a factor of 2? No. Okay. It's different. Oil is different. There's a lot more gas dissolved in the oil in Ecofisk. Okay? And the oil itself is changing differently than water. Okay? So the B factor for the soda pop is not very big. It's like 1.001 or something. It doesn't shrink very much. But in oil, it can shrink as much as a factor of 3. Smurbuksur, out here, close to a factor of 3. Does that seem good or bad? The higher the factor. Bad. You only get a third of every cubic meter you find down in the reservoir. You only get a third of it out as sellable oil. But on the other hand, you get, for Smerbuk South, 600 standard cubic meters of gas for every cubic meter of oil. Now, gas is having a larger and larger value now in the marketplace. It's not as good as having oil, but it's not bad. Okay? So that's this oil formation volume factor, and it's a very important term, this BOI. So this is the expression for the initial oil in place. Now we've got an H. Of course, the thickness can vary over the area, and so it's actually, this is a big integral where H is changing in space, the area in the area space. Water saturation, as we'll talk about today, can be varying as a function of area and depth. So this average water saturation is a spatially integrated average. A spatially integrated average. Likewise, the thickness. And we'll also talk today about the fact that the BO term doesn't have to be constant from top to bottom of the reservoir. Okay? It could vary from 2.2 to 1.8. So in fact, this actually should be some kind of an average as well. This is the equation for getting the initial oil in place. And if we then look at the surface gas, initial gas in place, we get a term that's similar. We get an average H, an average phi, an average area, and a 1 minus SWC, which is in reality an average gas saturation, and divided by what we call VG at initial conditions. And this also could be an average, although that usually is a fairly constant number. I mean, it's this term here is the hydrocarbon pore volume of reservoir gas. So the average thickness in the reservoir gas part of the reservoir could be 13 meters, and the average thickness in the oil part of the reservoir could be 68 meters. Okay? So we're integrating a given phase, the reservoir oil or the reservoir gas. Okay. And the BG is exactly the same. It's if you start with 1 cubic meter of reservoir gas, how much surface gas do you get? Up here we said this ranges from 1.1 to as much as 3. And for gas, it ranges anywhere from about 1 over 50 to 1 over 400. Okay? And the reason I write it that way is because you can remember the term 50 and 400, but you don't remember if I write it in a decimal, right? What 50 says is that you've got, for every reservoir cubic meter you have in the reservoir of gas, you get 50 standard cubic meters at the surface. Okay? That's a low pressure. This would be a low pressure reservoir. And this would be something like Kristen, or maybe it's only 300. Very high pressure reservoir. In fact, probably 400 would be the absolute maximum probably anywhere in the world. Okay? Is it clear what we're doing? Yes. Yeah. Okay, we're talking, the way we describe this reservoir now is that we've got basically two volumes. One that only contains oil and water, and another that contains only gas and water. In fact, there is probably a part of the reservoir transition between oil and gas, but it's usually a very thin zone. It's not very thick, where you have both gas, oil, and water in the same pores. So that's usually not a big term. Okay. Well, this is the simple way to calculate initial surface gas and initial surface oil in place. It's not right. Okay? It's part right. It's not wrong, but it's only part right. And let's take Ekofisk as an example. Okay? Ekofisk is about 12 billion barrels of reservoir oil. 12, write it down. Let's just do a little example here. Okay? Ekofisk. It has an initial hydrocarbon pore volume of approximately 12 billion, which is 12 10 to the 9th, reservoir barrels. Sometimes we write that as RB, reservoir barrels. How much surface oil, if I could play God and take all of that oil to the surface, how much surface oil would I get? Would I expect to get? 6 billion barrels. Okay? So if we say that the BOI is approximately 2 reservoir barrels per stock tank barrel, STB is stock tank, and a stock tank is a log, okay? Stock tank barrel. That's the same as a surface barrel, because we have these tanks at surface conditions. So reservoir volume per surface volume is a factor of 2. That means that our initial oil in place from our equation is what? 12 10 to the 9th divided by 2, which is about, well, this is, because these are approximate, this is approximately, but this is equal to 6 billion barrels. Today's price of oil, of course, it's on the way down, but it'll go back up and on and on. Let's say it's $60 oil, $60 per barrel. How much money is that? If you got all of it out, 60 times 6 is $360 billion, times 6 crowns, just to make it easy for you. Okay, 360 billion barrels times 6. $2,000? Is that right? 2,000? 360 times 6. Help me out. Okay. Around 2,000 billion crowns, which is 2 000 miljard kroner. Okay? 2 000 miljard kroner. Now, we might get in Ekofisk, we're going to be lucky because it's one of the world's most successful water-enhanced oil recovery projects anywhere in the world. So we might get 50% of that out. Still a lot. Of course, we didn't get $60 oil in 1970. Okay? But if we're lucky enough to find a new one, you start seeing the amount of money we're talking about. Okay? But the problem with what I'm trying to get at is that Frigg, which is the first large gas field in Norway, Frigg, and it's gas only. This is oil only. So the hydrocarbon pore volume of reservoir gas here is 0. And here, I'm going to kind of make some guesses. The initial gas in place in Frigg was about, just to make a simple number, about 6 times 10 to the 12th, what we call standard cubic feet, standard or surface cubic feet, and if we say the BG in Frigg initially, I'm going to guess here is probably 200, 1 over 200. Well, we don't need to make this calculation. Let's just stick with this. Then you've got some kind of a hydrocarbon pore volume in Frigg, which is reservoir gas hydrocarbon pore volume, which is about 6 10 to the 12th divided by 200. Or, let's see, times 200. Times 200. Divided by 200. It's early. Okay. Let's see, from the equation, initial gas in place is equal to hydrocarbon pore volume divided by BGI. So that's BGI times initial gas in place. So it's initial gas in place times BGI. So that's 6 10 to the 12th times 1 over 200. Okay? And that's equal to 3 10 to the 10th cubic feet. Okay. Okay. That's another field. Initial gas saturation 0 in Ekofisk. Initial gas saturation in Frigg is probably about 80%. Initial oil saturation in Frigg, 0. Initial oil saturation in Ekofisk, maybe on average 0.8. Now, if we use the equations that we just talked about with this geologic picture, we get the average H and the average area and the average porosity and the average saturation. We get these numbers. The equations give you these results. But there's a small problem. I say small. I'll put it up here. In Ekofisk, there's a small problem. Because it ends up that in Ekofisk, strangely enough, that there's an initial gas in place of approximately 6 times 10 to the 12th standard cubic feet. But there is no gas saturation. Okay? Something's strange. Something's wrong. with the equations that I just gave you. There is no gas saturation in Ekofisk, but it's got 6 trillion cubic feet of gas, just like Frigg, which was one of the big. It's not quite as big as Ormen Lange, but it's still big. Ormen Lange is about 10 of these 10 to the 12th standard cubic feet. So where is all that gas coming from? Where's all the gas coming from? Come on, you guys. I know it's early. Anybody here from Tromsø? You have an excuse to. Yeah. See, he has an excuse to not be thinking this morning. Did you watch the game? Did you watch the game? The soccer game last night? I mean, Daniel Broughton has always been my hero. I mean, I think he's just God's gift to Trondheim. Was it fantastic what he did? Did you watch the television or go to the game? No, you probably didn't see it close enough. And they didn't show it on the reports this morning. This guy was incredible. I was trying to find it for you to show. Instead of lecturing this morning, I was just going to put it on repeat. Did anybody else see it on TV? Was it wonderful? I mean, score, no score, win, no win. I mean, this guy was having fun. He was like heading it through 3 of these Tromsø players, heading it 5 or 6 times, like this, running at the same time, avoiding the 3 players, and then passes it in to the guy, to his colleague, who was so shocked that he missed the ball when he tried to kick it in the goal. But I mean, it was really beautiful. It was, my wife was rooting for Tromsø because she's from up north, but I'm not sure why I got. Oh yeah, nobody has an excuse except him to not get this answer. Okay. What did we say about Ekofisk? Every cubic meter of oil that comes out of the ground gives us 2 things, right? It gives us a half a cubic meter of sellable oil, and it gives us 300 cubic meters of sellable gas. I don't know if the numbers go up right, but you've got, I put 6 10 to the 9th. I hope the numbers come up right here. 3,000, 6 billion times, be about 1,000 cubic. Well, it's not exactly right, but basically this is the solution gas. The solution gas. You have to be a little bit careful here because I'm mixing units. This is stock tank barrels. So you got barrels and cubic feet and actually this number here, 6, should probably be bigger than that. It should probably be something like 9 actually. But I'll put that. If it's 9 or 6, it doesn't matter. It's a big number. Okay? So we need an additional term for our initial gas in place, right? This is only one part of it. This term only represents the so-called free gas in place. What we have to do is we have to add a second term, which is the initial oil in place times what we call the solution gas oil ratio. RS is the solution gas oil ratio. All of the gas oil ratios in petroleum are written with the term R. GOR, and its symbol is simply R as a symbol. So this solution gas oil ratio is, if you take an oil from a reservoir to the surface, it gives you two products, a sales gas and a sales oil. The ratio of those two volumes at the surface is what we call RS. Volume of sales gas over volume of sales oil. But this is coming from a reservoir oil at the reservoir. This term is called the initial gas in place, coming from the reservoir oil. Coming from the reservoir oil. So you have you get surface gas from two places. You get it from free gas being produced, and you get it from free oil being produced. And in that free oil is this dissolved gas which comes out at the surface. Is it clear? Or not quite? And you've got the same for oil. Now in the case of frig, the amount of solution oil dissolved in the gas initially, it's like this air in here. If we took the air in here and we cooled it down to a low temperature, what would we get out in the cup? Could we drink it? Come on. What would we get in the cup? If we put a cooler right here, circulated the air, and we got all the air, we dried the air, what would we get in the cup? Water. Could we drink it? I'm not sure. Yeah, you can drink it. It's just the same kind of water out on the ground there. It's a little bit cleaner than on the ground. Okay? We drink it. It's water. Dissolved in the air. The same thing is in reservoir gas. Is at high pressure and high temperature, and there's some of the and then sometimes there is oil dissolved in that gas. Sometimes not. In frig, not really. Not enough to make any difference. If you go to Kniston Field, just opened on Thursday last week, officially, with the cutting the scissors and everything. Go to Kniston, it's gas in the reservoir, 900 bars initial pressure. When it comes to the surface, it gives you lots and lots of oil. The amount of money we make from Kniston, which is a gas reservoir, the amount of money we make today, every day, you and me, taxpayers in Norway, right? Every day, half of that money coming from Kniston comes from oil. There's not a drop of oil. There's not any oil saturation in Kniston. It's all gas. But when it comes to the surface, it condenses out a lot of oil. And that oil we call condensate. It doesn't matter what it is. It can be brown, or it can look like water. It can look like what you get in the bathroom. Yellow, can be orange. It doesn't matter. It's a liquid. You put it on the tanker with the oil, and they pay you $60 a barrel. And in some fields, you get a lot of that condensate together with the gas. And Kniston's an interesting case because half of the value of the field is coming from this condensate, this oil. So we need another term for the initial surface oil in place. So what I'm going to do is, I'm running out of space here, so I'm going to say that now we're going to rewrite initial oil in place total is equal to this initial oil in place coming from what is actually reservoir oil plus initial oil in place coming from what is actually gas in the reservoir. So in the case of crystalline, that's a big number. Likewise, the total initial gas in place in a reservoir is the initial gas in place in the reservoir gas, that's usually the main term, plus the initial gas in place from the reservoir oil. In the case of Ekofisk, it's a big, big number. Bigger than Frigg, which is a pretty big gas field. So the point is that we've got two components, and the one component is what I'll refer to as, this is the free phase, and this is the solution phase. Okay? So you're getting surface oil from the free oil phase plus surface oil from the solution phase. And both of these here are related to a hydrocarbon pore volume divided by a formation volume factor. And these terms are basically the same hydrocarbon pore volume divided by B, the same exact term, times this ratio or divided by the ratio. It depends what you're looking at. Well, I don't know exactly how to write it, but it's either the solution gas oil ratio. Just a second. No, this is not right. In the case of initial oil in place, it's well, up here it's multiplied times little rs, which is little rs is just oil gas ratio. Big RS is gas oil ratio. So I'll write that for you. And then here it's times big RS. I know this is all getting confusing, but the little RS term, which is used up here, little RS is the solution oil gas ratio. That's the cup of water in the air. You're getting a liquid from a gas. And down here, we're using the initial gas in place from the reservoir oil in Ekofisk was this big number, right? And the RS was like the 300 standard cubic meter per standard cubic meter number. The point that you need to remember is that the source of this oil and gas we sell comes from two sources. Okay? That's the thing you need to remember. The details. Okay. So let's just sketch a little picture and see if you conceptually think you could water, oil, and gas. We say this is 5 kilometers. This is 2 kilometers. This is 25 meters. And this is 75 meters. If we say the water saturation here is 0.25, 0.35 on average, porosity 0.18, 0.22. That's probably not making sense here. I'll put 0.22 and 0.18 here. And we say that the little rs here, actually what I'll do is I'll make it a little bit complicated for you. I'll give you a gas-oil ratio instead. And I'll give you 600 standard cubic meters per standard cubic meter. And I'll give you an RS down here, which is equal to 400 standard cubic meters per standard cubic meter. Now, it's obviously a simplified geometry, but it doesn't take you a lot of fantasy to create a strange-looking, three-dimensional object that has this average area and average thickness and etc. Okay, if you have a little bit of fantasy. With these numbers, and if I had if everybody who has a calculator with them? Couple of you, okay? Okay, because it used to be everybody brought calculators. Now nobody brings calculators, so I can't give you a problem in class. But when you go home today, you should be able to calculate the initial surface gas in place and the initial oil in place for this reservoir from these numbers. These are the only numbers you need. And I highly recommend, if you're really wanting to learn from this class, introductory, that you make this simple calculation. Now, I've given it to you in metric units, but for you to compare with the numbers I've been talking about, Ecrifisk and Frigg and everything, you might have to convert it to barrels and cubic feet. If you want to do that, there's 35.31 standard cubic meters in, standard cubic feet in a standard cubic meter. And there's 6.28 stock tank barrels in a standard cubic meter of oil and gas. Okay? That way you can convert from your final numbers to the numbers that I've been talking about. Okay? So you have to calculate the initial gas in place of the free gas. Inside that gas, I can guarantee you there's a lot of condensate or oil, worth a lot of money. You've got to calculate the initial oil in place down in the reservoir oil. But in that, there's a lot of solution gas, worth a lot of money. And you add them all together and you get the total initial fluids in place, surface fluids in place. And if you do it successfully, then you can at least be a geologist. Because the geologist, this is the only time they use a calculator, is to do this calculation. Okay. Any geologists in here? No. Nikolai. But he has a calculator, so maybe there's hope for that. These are the new age geologists. They actually use calculators. So. Okay. Any questions before we take a break? Now, after the break, what we're going to talk about is how to get these average saturations, how the distribution of water saturation varies with depth, for example, and a little bit about the PVT properties, in particular the BO and the RS, how those also may change with depth. So these average numbers used in the equations, they come from somewhere, and we're going to talk about where they are and when there's a big variation, why is there a variation of water saturation. We're going to talk about those kind of things after the break. The spatial distribution of the properties. Okay? Okay. Anybody run out of things to do during the break and calculate the initial gas and oil in place? All right. Do you want me to do it for you in Excel? So you have an answer or not? That's up to you. Okay. All right. All righty. Let's see here. Let's see. We've got reservoir gas, and then we've got H, area, P, porosity, SWC, what else? B, GI, and then reservoir oil, and we got the same things. So just put in and that would be BOI or SI. You need little RSI. Actually, that's put that there. Okay, we got meters, meters squared, cubic meters per standard cubic meter, standard cubic meter per standard cubic meter. That. Okay, we got 2575. 25. Area is 2 by 2,000 by 5,000. Stuck keyboard here. Okay, and then we got porosity was 22% in the gas. Water saturation was 0.25 in the gas. BG was 1 over 250, I think. 1 over 250. And the solution gas condensate ratio was 600. Okay, and then thickness here was 75. That's the same as up here, area. Doesn't have to be in the gas and the oil. They can be different areas. Porosity was 18 and 35% water saturation in the oil zone, 1.8 formation volume factor, and 400, which is very high solution gas-oil ratio. Okay, so basically we want to calculate over here the initial teach you some good practice, spreadsheet practice. Everything that you input in the way of data is in red, so I know next time if I come back next year to teach this same course, I don't have to remember. Everything in red in my spreadsheets is what I have to input. Okay? It's the only way to... I don't want to make this red because this is linked up to here, right? Now it could be different. It could be... Maybe we should have it as red because it could be different for the reservoir gas and the reservoir oil. Okay? So I'll put it as red so I know it's input. So now we're going to calculate okay. This is Daniel Brolton. You don't believe me? I got a picture of him here with my son. I sent him to the game yesterday. Got a picture with Daniel Brolton. You don't see it? It's kind of small. Yeah. He's got his arm around him, my little boy. And then when he left, he did this to us on his head. You know how he always does this to the players? And I figured, well, you know, he got in, you know, it's true. So now we're going to have dinner. Okay. All right. So let's calculate hydrocarbon pore volume for the reservoir oil, and then initial oil in place from the reservoir oil, and then we'll calculate initial gas in place. Let's see here. How do we want to do this? Let's move all of the cut, insert. I'm going to put all these at the top. Okay. Initial gas in place, initial oil in place, initial gas in place from the reservoir gas. These are based on hydrocarbon pore volumes. The initial oil in place from the reservoir oil, and the initial gas in place from the reservoir gas. We calculate those first. Okay? We'll say based on hydrocarbon pore volumes of the reservoir. This is going to be based on the hydrocarbon pore volume of the gas. And then below that, we'll calculate the initial oil in place from the initial gas in place from the reservoir oil, which is a solution, and the initial oil in place from the reservoir gas. Solution. Gas oil ratio, RS, I, and the solution, okay, and that's in the reservoir oil, and that's in the reservoir gas. Yeah, I thought I was big enough, but here I'll try to make it. Is that better? Okay. I'm recording this, so you can just, if you want to go back and follow it. I mean, the point is that we're going to get 2 initial oil in places, 2 initial gas in places. But the first one we calculate is based on hydrocarbon pore volume. So that's these 2 here. Calculate these first. Once we have these 2, we can calculate the solution initial gas in places. And then we'll get the totals. Initial oil in place, total. like that, and we'll just add them together. And all of these are going to be standard cubic meters. See, my hope is to get Don Gibraltar to start in petroleum engineering when he finishes playing around. That's my hope. So I gotta start working on his math skills. Okay. So basically, we go down here. The initial oil in place from the reservoir oil. We have to go down to the reservoir oil part. We got the thickness, the area, the porosity, the 1 minus water saturation there, and then divided by the BOI. There we go. And that's going to be a big number, so I'm going to put it into a kind of a scientific format. I like to do this. Okay. Now watch. All ready? This is like magic. See, that's your life salary, flipping back and forth. Your life salary. Okay. Just kind of put it in perspective. Okay. It just went away. All right. So that's the initial. Now let's calculate those numbers in units that we're used to here, or you're not used to them, but I am. Stock tank barrels. All the places with oil, I'm going to put barrels, and I apologize for that. And then standard cubic feet for gas. Okay. And that's this number times 6.28. That's 306 million barrels. Not bad. That's it's a small field in Norway. It's a monster field in Oklahoma. So it's 306 million barrels. So it would just kind of make it in Norway. And gas in place, same kind of thing. We go down, we get the, except it's right here, thickness times area times porosity times 1 minus water saturation divided by gas formation volume factor, which was this 1 over 250. And I'll use the same format here, there. And I'll convert it to my units. That's a third of a TCF, and that's a small gas. I mean, hardly worth developing gas field. In of course, this is a you could never develop this kind of size gas field in Norway by itself. But between the oil and the gas together, it might be a satellite field. If you already have an infrastructure close that you can send the gas and oil to be processed at some other facility, you couldn't pay for a big development with this size of field. So let's see how much extra oil we get from what's in the reservoir gas. Okay, so we take the reservoir gas in place, surface gas in place here, and then we're going to divide by this 600 number. The 600 number says that if we take reservoir gas up to the surface, we get 600 units of sellable gas for every unit of sellable oil. So now we know that the total sellable units of gas is right here. It's 10 to the 10th standard cubic meters of sellable gas. So if we divide by the 600, we get the theoretical sellable condensate for sellable oil. That divided by this 600 number. Oops, that was not what I wanted to do. I want that to be down here. This divided by that. Okay, and we want, that's, oh no, that's not what we wanted. That's supposed to go here. The initial gas in place, this was the initial oil in place for condensate in the reservoir gas. Now we're going to look at what gas is in place but in the reservoir oil. And that's this number times the gas-oil ratio down here, 400. So, okay. I'm going to reverse these two, the order of these two here. Just give me a second. Okay, so it's kind of we got that. Boy, that was good. Yeah, so that's initial oil in place, reservoir gas. So let's just take these and copy those down. So now you see that there's about a third as much oil inside the gas as there is oil itself. Okay, see this is 100 million barrels of condensate versus 300 million barrels of free oil. So we're almost at 500 million barrels, which is getting to be good size. Not big, but good. And gas, if you look at the gas, you actually have more gas in the oil, in solution in the oil, than you have free gas. You see that? You've got 7, your units you're probably used to here, 200 billion standard cubic meters of gas in solution in the oil, and you've only got 1 billion cubic meters of gas, free gas. So there's more free gas, there's more gas in solution than there is free gas. It's like Ecofisk, a lot of gas in solution in the oil. So now we just add the two together, totals. We got 1 TCF of gas. That's the size gas field you have to have in Norway to consider a small-scale local development. About 1 TCF, about 300 billion standard cubic meters. So it's at the for a gas field development. For oil, we're at almost 500 million barrels. So this field would be economic in Norway, unless it's way off by itself. I'll save this in the course thing. I'll put this out somewhere on the internet. And this course, I'm trying to get into its learning. I don't know who's in control of it yet, but once I get it, I'm going to post. So initial fluid in place, that's the spreadsheet. Then you can go in here and change the numbers here. Let's just put in, just for the fun of it, Ecofisk. Okay? I don't know the area of it. It's the only thing I'm not sure. But just for the fun of it, the gas, what we said was 0, right? Goodbye. No gas. No free gas. Right? We got rid of the free gas. None. And then on the oil, it's pretty thick. It's like maybe on average 200 meters thick. I'm not sure about the aerial size, so I'm going to say probably more like well, it's up here. It's input up here. I'll put it down here. I'll probably say it's kind of circular. There's a salt dome that comes up, and it's kind of a circular thing. So I'm going to guess 8 by 8 kilometers. I don't know. We're going to see if it comes up with some numbers that 8 by 8 kilometers. This. Porosity. Okay, porosity. We got, what was it? High? Chalk? 35%. Water saturation was low, maybe on average 15%. What do we talk about here? Equifax 2. And there it was about 300. That's a little high, so it's maybe like 250 is probably a better average. Okay? Now, how many billion barrels did I tell you? Equifax, initial in place. Around 6 billion barrels. So let's see if we got something close to that. 11. Not too far off. I was going to say 5 by 5 kilometers, but I thought that's a little bit small. So what do we have here? We got 8 by 8. Let's try 6 by 6. There it is. 6 by 6 kilometers. That's what in headings left for you guys, you know, they're healthy. Okay? 200 meters thick, high porosity, low water saturation, 6 billion barrels. What kind of gas in place? 9 TCF. It's big. It's okay. Okay. Anyway, these are the kind of numbers that you have to come up with. And now we're going to talk in the last 20 or 30 minutes about how these numbers we come up with them. Okay? Any questions before we leave this? I will post it and you can have it. Okay. So the first thing that most people are concerned about is the connate water saturation as a function of depth. Now, I'll make two comments. For medium to high permeability, okay, reservoirs, and we're talking maybe probably greater than 10 to 100 millidarcies, which is most of the fields in Norway. Equifisk is not because it's chalk and it's low, but it has fractures. But in general, what you get in the way of water saturation versus depth is something that looks like that. And this zone here, which is called the transition zone, from 100% to irreducible water saturation, is small relative to the total thickness. It's not zero, but it's what we'll say is that it is much less than the total thickness of the reservoir unit. Maybe 3 meters, 5 meters. The higher the permeability, the shorter it becomes. And I'll try to explain why. If I stop talking so much about soccer. In low K reservoirs, we get something that looks totally different. Irreducible might be over here, 100%. This is SWC, depth. And what you see is that even at the top of the reservoir, it may not be completely down to irreducible saturation. Now, here what we're seeing is basically a large transition zone. Now, it may be such that all the way down to maybe here, the mobility of water is close to zero. If we put a well there, we produce it, we only get oil. Okay? And what I should say is really low K oil reservoirs. And we'll come back to why it's, you very seldom get a very long transition zone in a gas. And I'll explain to you why here in a second. Down here, the water mobility is enough to where it will produce in some amount. So obviously the average in this case is essentially, if we look at the average water saturation in this case, a good average is right here. And then we just simply say this is our gas-water contact approximately. And this is our average condensate saturation. Here, down here, it's much more difficult because the question becomes of the oil in this here. Now this is our oil saturation, right? What is actually going to flow? I mean, how much is really available to produce? So here the big question is, what is the average condensate water saturation? Okay. Well, you might just take water oil contact, and you might just take the entire average over the entire interval, but very likely much of the oil down here is inaccessible. Because it has very low oil mobility. The water saturation is so high that the oil has a hard time flowing. Now you don't understand why it's like this, but I'm going to try to give you in a 5 or 10 minute explanation of why does the water saturation vary with depth. Okay? And I hope from these two examples you can see where it doesn't really matter much here, but it has a big effect down here. So let's look at is how and why water saturation initially varies with depth. And we're going to stick to oil reservoirs because that is where it's most important. Okay? It works like this. On Monday we talked about the fact that if we plot pressure versus depth, initially when we find the reservoir, the water pressure versus depth will follow a straight line. This is water pressure versus depth, And it's basically the slope is proportional with the density of the water times G. Okay, that's the slope of that line. It doesn't look like a straight line, but let me try to redo it. Try to get a straight line. Okay? That's it. It's a straight line. Also for the oil, but a different slope. And that's the pressure of the oil. This, as we talked about before, is what we call the water-oil contact. Sometimes it's written oil-water contact. That is where the water pressure equals the oil pressure. And again, the slope of this is proportional, or actually equal to, the slope is equal to the density of the oil times G. That's the way it is. Now, in a rock like this, a bigger piece here. This is our reservoir, Ecophyst reservoir. There's an equilibrium between the gravity forces here, these are pure gravity forces, and what we call capillary forces. Does anybody know what capillary pressure is? Have you learned about capillary pressure yet? Is that a, I don't really know, or? Okay. The pores in this rock, we talked about the distribution of the sizes. So one way to look at, Torshatter is going to talk to you about this, but one way to look at this rock is that the different pore sizes, remember diameter of pore, it went from about 0.1 to 1 micron for chalk, right? And it had this distribution that was like that. Okay? One way to look at this as a pretty good assumption is that we basically have, we can break it into 10 straws, pipette, 10 capillaries, very small, okay? Isolated from each other. So what we're going to do is that we're going to take a thing of water like that, a container of water, and we're going to put in here and I'm going to go to the largest one. Okay, this diameter here is 0.8 microns. And this one here is 0.2 microns. Okay? And we just create, according to the frequency of what kind of capillary we have, we just say that these are like individual capillaries. If I make a beacon, a bowl of water, and I put these very small capillaries in, the water level will rise highest for which one of these? The one on the left, right? So we get up to here. So this one's going to fill in with water all the way to the top, like that. This is water. This one is going to fill up like to here, right? And this one's going to fill up to like there. Okay? this model is called a bundle of capillaries, and it's a pretty good approximation for. Now the point is that this is also an experiment where you have a balance of forces between the gravity forces and capillary forces, right? And based on this frequency plot in our experiment, there might be 3 of these capillaries, there might be 7 of these capillaries, there might be 2 of these capillaries, right? In the middle, we might have 15 of these capillaries, this size. Okay? If we go to some height, if we just pick a height like that, then what we can say is at that height, we know the water saturation because we know the pore volume of all of the capillaries all the way across. 2 of these, 15 of these, 7 of these. These capillaries are full of water at this depth, Z. These capillaries are full of oil, the other phase. Okay? And this is what's happening in the reservoir. You're getting a balance of the gravity forces, which I've drawn here, and the rock itself has a capillary pressure curve, which is approximated by a bundle of capillaries. So at this particular depth, the average saturation of water at that depth is equal to basically the sum of the what would be pi d squared of the capillaries filled with water, right? And I'll just write that W. Any capillary that's filled with water, it's the sum of those areas divided by all of the capillaries. Okay? That's the average water saturation at that depth. Okay. Now, what we actually do is we actually construct from measurements like this on a core like this, you can actually measure this kind of distribution. And then what we do is that we actually we convert. We have what's called a capillary pressure curve. For a piece of rock. And we say that the capillary pressure is basically equal to this is who wrote this equation? I can't remember. Ask Torstetter. I don't remember who. But this is the interfacial tension between, in our case, what we're looking at, between the two phases in this capillary experiment. Okay? Between, in this case, it would be air and water in our experiment here. And this is the radius of the capillary. So we can convert the pore size distribution to capillary pressure distribution. And then that can be based on this particular diameter. We can say that all of the capillaries, all of the pores that size or smaller, are full of water. So this has got a certain saturation associated with it, water, wetting phase. Okay? So if you take one particular capillary, you can use the same experiment and say that at this particular size capillary, all of the capillaries of this size and smaller are full of water. So if we pick a particular capillary size, which is the same as picking that, we know its capillary pressure, PC, and we know what percentage of all of the capillaries are full of saturation with water. So we get this relationship between capillary pressure, which is the air pressure in this case, minus the water pressure at this particular point. That's the air pressure and water pressure. So this is actually measured in the laboratory. There's different ways to measure it. But the point is that we have a relationship between capillary pressure between two phases, and we can convert the air-water curve to an oil-water curve. Air-water. By simply taking the interfacial tension difference. This would be oil water over air water. So this is our lab measurement. This is what we need for our field oil water. And this is basically a phase behavior, a fluid property. And air water is typically around 70 millinewton per meter. And oil water interfacial tension typically ranges from 20 to 50 millinewton per meter. So there's a correction of a factor of 2 or 3. Now, so now we know capillary pressure between oil and water as a function of water saturation. This is a given. We know this. That, we know by definition, is the oil pressure minus the water pressure. So now, if we go back to this figure here, what is this? Oil pressure, water pressure. So we know oil pressure is equal to, let's just say, the reference water-oil contact pressure minus density of oil, G, times a particular distance, Z, minus the water-oil contact. Actually, this would be, I need to change the sign on this. Water-oil contact minus Z. We got this pressure down here minus the oil gradient, right? So the oil pressure is equal to the water-oil contact pressure minus the oil head. Water pressure is equal to the same water-oil contact pressure down here minus density of water times the same distance. Right? So we know from our capillary pressure curve what the water saturation is at a given difference between these two. Right? But this can be written as oil minus water pressure. This cancels here, and we get G ZWC minus Z times density of oil. No, it would be actually oil minus, so it would be water minus oil. So at each depth, we know the capillary pressure. We know PO and we know PW, so we know the capillary pressure. From this capillary pressure curve, we know what water saturation is at that capillary pressure. So we know the water saturation associated with this difference. This relationship gives us water saturation as a function of depth. Hva som står i? Here, PC, this is capillary pressure, PC, W oil, water oil capillary pressure. It's the water oil capillary pressure. This relationship is known from laboratory. So all we need to know is the starting point here, the density of the oil and the density of the water. And then we can convert the capillary pressure curve into a saturation versus depth curve. Okay? I'm sorry I'm over time. Just give me 5 more minutes. This is the Daniel Brolton effect. I got excited. So now, okay, the transition zone, which is what we're really interested in, is controlled by 2 things. It's the level of capillary pressure, oil water, and the density difference, water oil. Okay? The transition zone is large for a high capillary pressure curve and for a small delta rho. So if the oil you have is a heavy oil, its density is close to water, and that delta rho becomes very small. Then the transition zone can become very long. Okay? So this would be for heavy oils. In Norway, we have very few of those. Grane, I think Ula, they're not Troll, but they're not really heavy, I mean, in the normal sense. When it comes to this high or low, I'll just show you a sketch. I'm sure Torsetter will show you and explain this more. It looks something like this. For a high permeability rock, it looks like this. This is a high permeability rock. I'm not going to put a scale on it. For a low permeability rock, it might look like this. Okay? And, of course, everywhere in between. Okay? So the point is that the low permeability rock has smaller pores in general, therefore higher capillary pressures. Chalk obviously has very high capillary pressures because of the very, very small pores, 0.1 to 1 micron. A sandstone rock, the smallest pore might be 3 microns. You go to 300 microns. So you get a much lower capillary pressure curve. Therefore, what we can say is that high PC means low, in general, low perm. Low permeability reservoirs tend to have high capillary pressures. So the worst transition zone, the longest transition zone will come from what? Heavy oil, low perm. In Norway, we have light oil, high perm in general. So why we even teach capillary pressure, I'm not sure. Okay? But that's okay. But you're going to go from Norway, you're going to go to all these places that have low perm and heavier oil in the Middle East, for example, other places, where it can become a very important factor. The entire reservoir may be a transition zone. Okay? I think that's all I'm supposed to teach you guys from what they gave me. They gave me a one line, what they want me to teach you. I think this is it. So I apologize for being over time because obviously I got excited with Daniel and then, I can't help it.